Roughly 4.6 billion years ago, the space currently occupied by our solar system was nothing more than a vast, freezing, and silent cloud of interstellar gas and cosmic dust known as a giant molecular cloud. This pre-solar nebula was staggeringly massive, stretching across several light-years of empty space. Its composition was overwhelmingly dominated by hydrogen. In the strict realm of chemistry and quantum mechanics, hydrogen is the simplest, lightest, and most abundant chemical element in the universe. Its atomic structure consists of a single positively charged proton in its nucleus, orbited by a single negatively charged electron. Alongside hydrogen, the cloud contained helium and trace amounts of heavier, complex elements, such as carbon, nitrogen, and iron, that had been forged inside the cores of ancient stars and violently ejected into space upon their explosive deaths. To understand how this diffuse, chaotic cloud of gas transformed into a highly structured solar system, we must examine the fundamental physical principles of gravitational collapse. In the early 20th century, specifically in the year 1902, the British physicist and astronomer Sir James Hopwood Jeans formulated a mathematical concept that fundamentally altered humanity's understanding of stellar formation. Jeans's importance in the field of theoretical astrophysics is absolute. He provided the foundational mathematical framework required to calculate precisely when a celestial cloud of gas will physically collapse under the sheer weight of its own gravity. He discovered a critical threshold known today as the Jeans Massachusetts. Written discursively, the physics dictate that the critical mass required for collapse is proportional to the square root of the temperature of the gas cloud cubed, divided by the density of the cloud, multiplied by specific gas constants. If a region of a molecular cloud exceeds this specific mass limit, the outward thermal pressure generated by the kinetic movement of its gas molecules is no longer mathematically sufficient to counteract the inward crushing force of its own gravity. Our specific pre-solar nebula hovered near this critical threshold for millions of years in a delicate, fragile hydrostatic balance. Modern astrophysical research, supported by the isotopic analysis of ancient meteorites, strongly theorizes that an external kinetic force disrupted this balance. A nearby supernova, the cataclysmic, terminal explosion of a massive, dying star, sent a violent, high-speed shockwave propagating through the interstellar medium. When this shockwave aggressively slammed into our molecular cloud, it violently compressed the gases, pushing localized regions well over the Jeans mass limit. This triggered an unstoppable, localized gravitational collapse. As the localized pocket of gas collapsed inward upon itself, the fundamental physical law of the conservation of angular momentum dictated its shape. Just as a figure skater spins drastically faster when pulling their arms into their body, the shrinking cloud began to rotate with increasing violence. The centrifugal forces generated by this rapid rotation caused the spherical cloud to flatten out into a colossal, spinning accretion disk. At the exact geometric center of this rotating vortex, the vast majority of the collapsing mass accumulated. The immense kinetic energy of the infalling gas molecules violently colliding with one another was rapidly converted into thermal energy, creating a superheated, glowing sphere of plasma known as a protostar. For roughly 50 million years, this primitive protostar continued to forcefully cannibalize the surrounding disk, sucking in mass while its internal temperature and barometric pressure rose exponentially under the crushing weight of its own gravity. Eventually, the core temperature of this dense protostar reached an incomprehensible 15 million degrees Kelvin. At this extreme thermal threshold, the fundamental laws of nuclear physics took absolute control. The German-American theoretical physicist Hans Bethe published groundbreaking, highly complex research in the year 1939 detailing the exact mathematical and quantum mechanisms of stellar nucleosynthesis. Bethe's work was of monumental, paradigm-shifting importance. He was eventually awarded the Nobel Prize in Physics for definitively proving exactly how stars generate their immense energy through continuous nuclear fusion. In the crushing core of our nascent sun, the extreme heat and pressure provided enough kinetic energy to overcome the Coulomb barrier. In particle physics, the Coulomb barrier is the natural, intense electrostatic repulsion that occurs between two positively charged subatomic particles, in this case, hydrogen protons. Because they have the same electrical charge, they naturally repel each other. However, the extreme environment of the solar core forced these protons to smash together with such unimaginable velocity that the strong nuclear force took over, physically binding them together to synthesize a heavier element, helium. During this continuous nuclear transmutation, a tiny fraction of the original hydrogen's physical mass is completely annihilated and converted directly into pure electromagnetic energy. This violent reaction follows the foundational physical law formulated by Albert Einstein, mathematically defined, where the energy released is equal to the mass annihilated multiplied by the speed of light squared. The sudden, explosive outward thermal pressure generated by this continuous nuclear fusion perfectly balanced the inward, crushing crush of the star's immense gravity. Our sun was officially ignited, achieving absolute hydrostatic equilibrium, and violently flooding the dark, rotating disk of debris around it with brilliant. Surrounding the newly ignited sun was a colossal, rotating structure known as the protoplanetary disk. This violently swirling halo of residual gas and dust stretched across billions of miles of empty space. Within this chaotic disk, a severe thermal gradient existed. Close to the young sun, temperatures were far too extreme for volatile compounds, such as water, methane, and ammonia, to condense into solid ice. Only elements and compounds with exceptionally high melting points could survive in this blistering inner region. Consequently, the inner solar system became dominated by metals like iron and nickel, alongside silicates. In the realm of chemistry and mineralogy, a silicate is a highly stable chemical compound containing silicon and oxygen atoms, which physically bonds to form the vast majority of rocky crusts in terrestrial planets. To comprehend how microscopic grains of silicate and heavy metals coalesced to form the Earth, we must look to the pioneering work of the Soviet astronomer Viktor Safronov. In the year 1969, Safronov published a highly complex, foundational thesis detailing the mathematical mechanics of planetary evolution. Safronov's importance to the global astrophysics community is monumental. He essentially founded the modern planetesimal hypothesis, providing the rigorous mathematical models required to prove how microscopic dust grains floating in a vacuum can collide and stick together through sheer electrostatic forces. Safronov mathematically demonstrated that as these tiny clusters of dust grew larger, their collective gravitational pull increased. Over roughly 10 to 20 million years, these clumps violently collided and merged, growing into massive, kilometer-sized rocky bodies called planetesimals. In the chaotic inner solar system, millions of these planetesimals aggressively slammed into one another, driven by the kinetic mechanics of orbital physics. Through relentless cataclysmic collisions, a specific rocky sphere began to dominate its orbital path, sweeping up all surrounding debris. This growing sphere of molten rock was the embryonic planet Earth. During this period, known as the Hadean Eon, beginning roughly 4.6 billion years ago, the young Earth was a terrifying, boiling ball of magma. The planet was subjected to a continuous, apocalyptic bombardment of asteroids and comets. Every impact delivered an immense amount of kinetic energy to the planet's surface. In the physical sciences, this energy is governed by the mathematical equation where kinetic energy equals 1/2 of the mass times the velocity squared. Because the celestial debris was striking the Earth at speeds exceeding tens of thousands of miles per hour, the sheer kinetic energy was instantly converted into unimaginable thermal heat upon impact, completely melting the rocky crust. Simultaneously, the planet was being heated from the inside out by the aggressive decay of short-lived radioactive isotopes. In the strict realm of quantum mechanics and nuclear physics, radioactive decay is a physical process where an unstable atomic nucleus spontaneously loses energy by emitting ionizing radiation, fundamentally transforming into a different, stable element while releasing massive amounts of internal heat. This combination of relentless orbital bombardment and intense internal radiogenic heating triggered a profound planetary transformation known as the Iron Catastrophe. As the embryonic Earth grew, its internal temperature eventually exceeded the melting point of elemental iron, roughly 2,800 degrees Fahrenheit. Because heavy metals like iron and nickel possess a significantly higher atomic mass and physical density than the surrounding silicate magma, the fundamental law of gravity forced these molten metals to physically sink thousands of miles downward toward the exact geometric center of the planet. This colossal global displacement of trillions of tons of heavy liquid metal generated extreme internal friction, releasing an additional, overwhelming surge of thermal energy that completely liquefied the entire globe. This specific event differentiated the Earth into distinct physical layers, forming the dense, metallic core and the lighter, silicate rocky mantle. The formation of this metallic core was an event of absolute biological and physical importance. It initiated the geodynamo effect, a geophysical phenomenon where the continuous, convective churning of the liquid iron outer core generates massive electrical currents, which in turn project a colossal, invisible magnetic field deep into space, forever shielding the future planet from the deadly, atmosphere-stripping radiation of the solar wind. However, the young Earth was about to suffer the most violent single event in its entire planetary history. Roughly 4.5 billion years ago, the Earth was not alone in its orbit. A massive, fully formed protoplanet roughly the size of Mars, named Theia, was accelerating on a direct collision course with Earth. To explain this cataclysmic event, American planetary scientists William Hartmann and Donald Davis published the giant impact hypothesis in the year 1975. Their importance to the field of planetary science is profound. They mathematically solved the enduring mystery of the Moon's origin by proving that an oblique, grazing collision between Earth and a Mars-sized body would generate the exact physical parameters required to forge our lunar companion. When Theia violently struck the Earth, the impact occurred at an estimated velocity of 22,000 miles per hour. The thermal and kinetic energy released by this collision was so incomprehensibly massive that Theia was instantly and completely vaporized, along with a massive portion of the Earth's outer silicate mantle. Trillions of tons of superheated, glowing rocky debris were explosively ejected into space, forming a dense, burning ring of magma orbiting the heavily scarred Earth. In the freezing vacuum of space, the fundamental forces of gravity immediately took hold of this debris ring. In an astonishingly short period, calculated by modern computer models to be less than a single century, the orbiting fragments of vaporized rock and magma violently collided and coalesced together, actively accreting into a brand new celestial body. This newly forged sphere of cooling rock became our Moon. In its infancy, the Moon was incredibly close, orbiting at an estimated distance of only 14,000 miles away, appearing as a terrifying, gigantic, glowing red sphere in the primitive Earth sky, compared to its current average distance of 238,900 miles. This monumental impact physically tilted the Earth's axis, forever establishing the mechanics of our planetary seasons and stabilizing our rotation, setting the absolute foundation for a world that would eventually cool and harbor oceans. Following the cataclysmic forging of the Moon, the Earth was left as a highly unstable, rapidly spinning, and completely sterilized ocean of boiling magma. For millions of years, the planet radiated its immense internal thermal energy out into the freezing vacuum of space. As the surface temperature slowly dropped, the topmost layers of the molten silicate mantle began to physically solidify, forming a thin, dark, and highly fragile basaltic crust. To precisely understand when this planetary crust cooled enough to support solid rock and eventually liquid water, geologists search for the oldest surviving terrestrial materials. In the year 2001, the American geologist John Valley published a groundbreaking study detailing the analysis of microscopic crystals found embedded in the ancient sedimentary rocks of the Jack Hills in Western Australia. Valley's importance to the highly specialized field of geochronology and isotope geochemistry is absolute. His pioneering analytical techniques pushed back the confirmed physical date of a solid Earth crust and a temperate climate by hundreds of millions of years, completely rewriting the timeline of our young world. The microscopic crystals Valley analyzed were zircons. In the rigorous realm of chemistry and mineralogy, zircon is a highly durable, incredibly resilient nesosilicate mineral composed of zirconium silicate, meaning its molecular structure consists of zirconium, silicon, and oxygen atoms tightly bound together. Because zircon crystals are exceptionally resistant to extreme heat and chemical corrosion, they act as virtually indestructible microscopic time capsules. By utilizing uranium lead radiometric dating, a process measuring the predictable mathematical rate at which radioactive uranium isotopes trapped inside the crystal decay into stable lead isotopes, Valley and his team determined these specific crystals were forged roughly 4.4 billion years ago. Furthermore, the specific ratio of oxygen isotopes trapped within their atomic lattices provided irrefutable physical proof that liquid water existed on the Earth's surface at the exact time they crystallized. However, the origin of this water presented a massive astrophysical puzzle. The extreme thermal environment of the inner solar system during the planet's accretion should have vaporized all volatile compounds, leaving the Earth completely bone dry. Initially, planetary scientists theorized that continuous, massive volcanic eruptions released trapped water vapor from the deep interior, a geophysical process known as volcanic outgassing. While outgassing did contribute to the early atmosphere, isotopic analysis of our modern oceans, specifically the ratio of heavy deuterium to standard hydrogen, points to a massive, chaotic, extraterrestrial delivery system. Between 4.1 and 3.8 billion years ago, the Earth and the newly formed Moon were subjected to a devastating, relentless barrage of celestial debris known as the Late Heavy Bombardment. The craters on the Moon's surface today are the permanent, physical scars of this violent epoch. The mechanical cause of this apocalyptic bombardment was completely unknown until the year 2005, when an international team of astrophysicists, including Rodney Gomez, Harold Levison, Alessandro Morbidelli, and Cleomenes Tsiganis, published the NICE model, named after the city in France where they collaborated to run their supercomputer simulations. Their importance to the field of orbital dynamics is monumental. They mathematically proved that the giant gas and ice planets of our outer solar system did not form in their current, stable orbits, but instead aggressively migrated through the solar system, fundamentally altering the trajectory of millions of smaller bodies. According to the NICE model, Jupiter, Saturn, Uranus, and Neptune originally formed much closer to the Sun, surrounded by a dense, massive disk of icy planetesimals. Over hundreds of millions of years, their gravitational interactions with this icy debris caused their orbits to slowly shift. Eventually, Jupiter and Saturn, the two most massive planets in the solar system, drifted into a precise 2-to-1 orbital resonance. This means that for every 2 orbits Jupiter completed around the Sun, Saturn completed exactly 1. This precise rhythmic alignment generated immense, repeating gravitational pulses. The fundamental physics governing this interaction rely on Newton's law of universal gravitation, stated discursively as the force of gravity equals the universal gravitational constant times the product of the two masses divided by the square of the distance between their exact geometric centers. The combined, amplified gravitational force generated by this resonance violently destabilized the entire architecture of the outer solar system. It physically flung the massive ice giants, Neptune and Uranus, outward into the icy debris field known as the Kuiper Belt, aggressively scattering trillions of frozen comets and icy asteroids. A massive portion of this icy shrapnel was hurled inward, accelerating toward the Sun and directly crossing the orbital path of the Earth. Millions of massive, icy comets violently slammed into the young planet. Comets are essentially primitive, dirty snowballs composed heavily of frozen water and trapped gases. In the strict realm of chemistry, water is a highly unique chemical compound consisting of two hydrogen atoms covalently bonded to one oxygen atom. Because the massive oxygen nucleus strongly pulls the shared electrons toward itself, the molecule is highly polar, possessing a slight negative charge on one side and a positive charge on the other. This unique atomic polarity gives water anomalous physical properties, such as a remarkably high specific heat capacity, which would later become absolutely crucial for absorbing solar radiation and regulating the global climate. Upon striking the Earth's rocky crust at tens of thousands of miles per hour, the immense kinetic energy vaporized the comets instantly, filling the primitive atmosphere with unfathomable amounts of water vapor. As the cataclysmic era of the late heavy bombardment finally subsided, the global planetary surface continued to cool. Once the atmospheric temperature dropped below 212 degrees Fahrenheit, the physical boiling point of water, the massive, global cloud deck began to aggressively condense. What followed was a torrential, relentless global rainstorm that lasted for millions of years. The liquid water poured from the dark skies, rushing over the barren basaltic rock, heavily eroding the young crust, and pooling in the deep, massive impact craters and tectonic basins. This continuous deluge eventually forged the very first global, primordial ocean. Above this vast, dark, and lifeless ocean, a dense secondary atmosphere stabilized. It was incredibly heavy, highly toxic, and completely devoid of free, breathable oxygen. It was primarily composed of carbon dioxide, water vapor, and nitrogen. In chemistry, nitrogen is a highly stable, inert gas whose diatomic molecules consist of two nitrogen atoms bound tightly together by a remarkably strong triple covalent bond. This triple bond requires massive amounts of thermal, kinetic, or electrical energy to physically break, allowing nitrogen gas to safely accumulate and persist as a major, stable atmospheric component throughout the planet's entire violent history. Underneath this crushing, unbreathable sky, shielded by the magnetic field and submerged in a newly formed ocean of liquid water, the complex geochemical stage was finally set for the most profound physical transition in the history of the universe, the emergence of biological life. Beneath the crushing, heavy atmosphere of early Earth, the newly formed global ocean was a hot, toxic, and highly acidic cauldron completely devoid of biological life. The exact physical mechanism by which inanimate, inorganic chemistry transitioned into living, biological organisms is known as abiogenesis. To understand this monumental leap, the scientific community points to a profoundly important laboratory experiment conducted in the year 1953 by American chemists Stanley Miller and Harold Urey. The importance of Miller and Urey to the fields of physical chemistry and astrobiology is paramount. They were the very first scientists to successfully simulate the hypothetical conditions of the early Earth in a controlled laboratory setting, proving definitively that the complex organic building blocks of life could spontaneously synthesize from simple, lifeless gases. In their sealed apparatus, they combined water, methane, ammonia, and hydrogen gas. They then applied continuous electrical sparks to simulate the intense, violent lightning storms that continuously ravaged the primordial sky. Within a single week, the clear water inside their glass flasks turned a deep, murky brown. When they analyzed this liquid, they discovered it was teeming with newly synthesized amino acids. In the rigorous realm of biochemistry, an amino acid is a fundamental organic molecule consisting of a basic amino group, an acidic carboxyl group, and a unique organic side chain. They are of absolute biological necessity because they act as the fundamental physical building blocks of all proteins, which in turn construct the cellular machinery of all known life. However, modern geochemical analysis suggests that the early Earth's atmosphere was actually dominated by carbon dioxide and nitrogen, not the methane and ammonia used in the Miller-Urey experiment, making surface-level abiogenesis through lightning strikes highly inefficient. Consequently, modern astrobiologists and marine geochemists have turned their attention away from the storm-ravaged surface and plunged thousands of feet down into the pitch-black, crushing abyss of the primordial ocean floor. Deep along the tectonic fault lines, where the Earth's thin crust was violently fractured, ocean water continuously seeped down into the hot silicate mantle. This water was superheated by the underlying magma to temperatures exceeding 750 degrees Fahrenheit. Because the barometric pressure at these extreme depths is an unimaginable thousands of pounds per square inch, the water was physically prevented from boiling into vapor, acting instead as a supercritical fluid. As this superheated fluid forcefully erupted back up through the rocky crust, it carried massive amounts of dissolved heavy metals, hydrogen sulfide, and thermal energy, creating towering, chimney-like structures known in these pitch-black, extreme pressure environments. A revolutionary biological process called chemosynthesis occurred. Unlike plants on the modern surface that rely on kinetic solar energy to produce food, the very first primitive, single-celled organisms utilized the intense thermal energy and the continuous supply of inorganic chemical compounds erupting from the vents. These extremophile bacteria functioned entirely without sunlight, feeding on the rich hydrogen sulfide gas. Over hundreds of millions of years of rigorous evolutionary trial and error, a specific, highly successful microscopic organism emerged, known as the last universal common ancestor, or LUCA. LUCA was not the first living thing, but rather the most recent common ancestor of all current life on Earth. It was a simple, single-celled prokaryote, meaning its cellular structure lacked a distinct, membrane-bound nucleus to protect its fragile genetic code. For over 1 billion years, these primitive, anaerobic bacteria completely dominated the global ocean, remaining hidden in the dark depths. But roughly 2.4 billion years ago, a catastrophic, biologically driven global shift occurred. A new, highly aggressive strain of bacteria called cyanobacteria evolved in the shallow, sunlit coastal waters. Cyanobacteria achieved something physically and chemically miraculous. They evolved the ability to harness the kinetic energy of sunlight through a highly complex biochemical process known as photosynthesis. In the strict physical sciences, the chemical equation for photosynthesis dictates that 6 molecules of carbon dioxide combined with 6 molecules of liquid water, when physically energized by solar photons, are chemically transmuted into 1 molecule of organic glucose sugar and 6 molecules of free oxygen gas. This process provided cyanobacteria with a massive, virtually unlimited energy advantage over their deep-sea counterparts, allowing their populations to exponentially explode across the global ocean. However, this evolutionary triumph released unfathomable quantities of free oxygen gas into the water as a metabolic waste product. To the anaerobic bacteria that had dominated the Earth up to this point, oxygen was a highly reactive, incredibly lethal and toxic gas. Before this toxic oxygen could bubble up and fill the atmosphere, it aggressively reacted with the massive amounts of dissolved elemental iron that had saturated the global ocean since the iron catastrophe. In chemistry, when free oxygen interacts with dissolved iron, it triggers a rapid oxidation reaction, forming insoluble iron oxide, commonly known as rust. Over tens of millions of years, trillions of tons of this heavy, red iron oxide physically precipitated out of the seawater and sank to the ocean floor, forming massive, alternating layers of sedimentary rock. These colossal geological structures, known as banded iron formations, are the absolute physical proof of this planetary-scale rusting event, and they constitute the vast majority of the iron ore mined by human civilization today. Once the oceans were completely depleted of dissolved iron, the free oxygen had nowhere else to go. It began to violently outgas from the ocean surface, saturating the dense carbon dioxide atmosphere. This specific era is known as the Great Oxidation Event. It triggered the very first, and perhaps most devastating mass extinction in planetary history, completely annihilating almost all anaerobic life on Earth that could not hide deep underground or at the bottom of the abyssal oceans. The sky slowly shifted from a toxic, hazy orange to a brilliant, clear blue, paving the chemical way for the evolution of highly complex, oxygen-breathing organisms. The catastrophic biological success of cyanobacteria and the subsequent Great Oxidation Event completely altered the atmospheric chemistry of the planet, initiating a severe global climate crisis. Prior to the accumulation of free oxygen, the Earth's primitive atmosphere was heavily insulated by methane gas, produced in massive quantities by ancient methanogenic archaea. In the strict realm of organic chemistry, methane is the simplest hydrocarbon molecule, consisting of a single carbon atom covalently bonded to 4 surrounding hydrogen atoms. Because of its specific geometric molecular structure, methane is an incredibly potent greenhouse gas. It is highly efficient at absorbing the outgoing kinetic infrared radiation emitted by the Earth's heated surface, preventing that thermal energy from escaping into the freezing vacuum of space. However, as molecular oxygen aggressively flooded the atmosphere, it chemically reacted with this atmospheric methane, oxidizing it into carbon dioxide and water vapor. While carbon dioxide is also a greenhouse gas, it is significantly less effective at trapping heat than methane. Consequently, the planet's atmospheric thermal blanket was rapidly and violently stripped away. The global temperature plummeted, plunging the Earth into the Huronian glaciation, which lasted from roughly 2.4 to 2.1 billion years ago. This specific glaciation is widely considered by the modern scientific community to be the first instance of a snowball Earth. The concept of a completely frozen planet was mathematically and geologically formalized by the American paleoclimatologist Joseph Kirschvink in the year 1992, and later rigorously supported by the Canadian geologist Paul Hoffman in the year 1998 through extensive isotopic analysis of ancient rocks in Namibia. Their combined importance to the field of paleoclimatology is monumental. They fundamentally overturned the long-held assumption that the Earth's oceans had remained continuously liquid, proving instead that the planet's climate system could mathematically cross a tipping point, resulting in massive continental ice sheets accelerating all the way to the equator. During this snowball Earth phase, the highly reflective white ice sheets bounced the vast majority of incoming solar radiation back into space, a geophysical phenomenon known as the albedo effect. This created a positive feedback loop that locked the planet in a deep freeze. The Earth only escaped this icy prison because tectonic activity continued deep beneath the frozen crust. Massive volcanoes persistently erupted through the miles-thick ice, pumping millions of tons of carbon dioxide back into the atmosphere. Because the frozen oceans could no longer absorb this carbon dioxide, the gas accumulated over millions of years until the greenhouse effect became strong enough to violently melt the global glaciers, triggering a massive, super greenhouse hothouse world. In the warming, nutrient-rich oceans that followed this global thaw, a biological revolution of unimaginable complexity took place. Single-celled life evolved from simple, disorganized prokaryotes into highly structured, complex eukaryotes. To explain this profound biological leap, the American evolutionary biologist Lynn Margulis published a highly controversial, yet ultimately paradigm-shifting paper in the year 1967 detailing the endosymbiotic theory. Margulis's importance to the field of evolutionary biology cannot be overstated. She successfully challenged the rigid, classical Darwinian view that evolution was driven solely by random mutation and aggressive competition, proving physically that the highest levels of biological complexity were actually achieved through unprecedented cellular cooperation. Margulis mathematically and biologically demonstrated that the very first eukaryotic cell was forged when a large, predatory anaerobic archaean physically engulfed a smaller, highly efficient oxygen-breathing bacterium. However, instead of digesting the smaller bacteria, the two single-celled organisms entered into a mutually beneficial, symbiotic relationship. The larger host cell provided physical protection and raw nutrients, while the smaller, engulfed bacteria utilized the toxic free oxygen to generate massive amounts of metabolic energy. Over millions of generations, this engulfed bacterium physically integrated into the host's cellular machinery, ultimately becoming the mitochondrion, the biological powerhouse of all modern complex cells. In the strict realm of genetics, the absolute physical proof of Margulis's theory lies in the fact that mitochondria still possess their own distinct, circular DNA, completely separate from the DNA found inside the nucleus of the host cell. This endosymbiotic merger provided the massive metabolic energy required to eventually build multicellular organisms, animals, and eventually human beings. While biology was fundamentally restructuring itself in the oceans, the very rocky crust of the planet was organizing into a continuous, mechanical cycle of creation and destruction. The solid outer shell of the Earth, known as the lithosphere, is not a single, unbroken sphere, but is instead fractured into massive, jagged puzzle pieces called tectonic plates. The modern understanding of this planetary mechanism is heavily attributed to the pioneering work of the American geologist and oceanographic cartographer Marie Tharp. During the 1950s, Tharp meticulously mapped the completely uncharted, pitch-black floor of the Atlantic Ocean using early sonar data. Her importance to the global geophysical community is absolute. She discovered the Mid-Atlantic Ridge, a colossal, continuous underwater mountain range featuring a massive, central rift valley. Tharp's mapping provided the irrefutable physical proof required to validate the theory of continental drift, originally proposed by Alfred Wegener in the year 1912. Tharp's discovery proved that the Earth's crust is continuously being torn apart at these mid-ocean ridges. Deep within the Earth, the semi-solid, superheated silicate mantle behaves like a highly viscous, boiling fluid. Driven by the intense radiogenic heat of the core, immense convection currents slowly rise toward the crust. When this superheated rock reaches the bottom of the lithosphere, it physically pushes the tectonic plates apart, erupting as fresh magma to forge new ocean floor. As new crust is created, older, colder, and denser crust at the far edges of the plates is violently forced back down into the mantle, a destructive process known as subduction. This relentless tectonic engine constantly shifts the continents across the globe, driving the formation of massive supercontinents like Columbia and, later, Rodinia, fundamentally altering global ocean currents, atmospheric weather patterns, and driving the relentless adaptation of biological life. As the dynamic tectonic engine of the Earth continuously rearranged the global supercontinents, the biological landscape of the oceans prepared for the most spectacular diversification of life in planetary history. Roughly 541 million years ago, a biological event of unprecedented magnitude occurred, known as the Cambrian explosion. During this relatively brief geological window, almost all major animal phyla that exist today suddenly appeared in the fossil record, exhibiting highly complex biological architectures, including articulated limbs, compound eyes, and hardened calcium carbonate exoskeletons. To understand the sheer morphological insanity of this era, paleontologists rely heavily on a specific, monumental geological discovery made in the year 1909 by the American paleontologist Charles Doolittle Walcott. Walcott discovered the Burgess Shale, a highly unique fossil bed located high in the Canadian Rockies. Walcott's importance to the field of invertebrate paleontology is absolute. His meticulous excavation and classification of tens of thousands of fossils provided the irrefutable, physical proof that the Cambrian period experienced a sudden, massive explosion of complex, macroscopic life. The Burgess Shale is geologically unique because it perfectly preserved the soft tissue of bizarre, alien-looking marine organisms, such as the five-eyed Opabinia and the fearsome apex predator Anomalocaris. Despite this massive proliferation of life within the oceans, the vast continental landmasses of the Earth remained completely barren, scorched, and totally irradiated by the sun. 4. For biology to physically cross the boundary from water to dry land, the planet had to manufacture a global chemical shield. This shield is the ozone layer. In the strict realm of atmospheric chemistry, ozone is a highly reactive inorganic molecule consisting of 3 oxygen atoms covalently bound together. Its formation in the upper stratosphere is driven by the relentless bombardment of solar ultraviolet radiation. Ultraviolet light consists of highly energetic photons that possess enough kinetic energy to physically shatter the chemical bonds of standard diatomic oxygen gas, the 2-atom oxygen molecules produced by photosynthesizing marine life. When an incoming ultraviolet photon violently strikes a diatomic oxygen molecule, it splits it into 2 highly unstable, solitary oxygen atoms. These free, highly reactive atoms immediately collide and physically bond with unbroken diatomic oxygen molecules, synthesizing triatomic ozone. The importance of this ozone layer is of absolute biological necessity. It acts as a massive planetary filter, absorbing the vast majority of incoming lethal ultraviolet radiation. Without this chemical shield, the intense ultraviolet kinetic energy would physically penetrate the cells of any terrestrial organism, aggressively shattering the delicate atomic bonds of their DNA strands, causing catastrophic genetic mutations and immediate cellular death. By roughly 400 million years ago, the ozone layer had thickened enough to completely block this deadly radiation, allowing the first primitive plants and amphibious tetrapods to finally crawl out of the oceans and permanently colonize the dry, rocky continents. This terrestrial colonization culminated in the Carboniferous period, beginning roughly 359 million years ago. The Earth became dominated by colossal, globe-spanning swamp forests of massive ferns and scale trees. These ancient plants evolved a revolutionary, highly complex organic polymer known as lignin to provide the rigid physical structure required to grow hundreds of feet tall against the downward pull of Earth's gravity. In organic chemistry, lignin is an incredibly dense, highly cross-linked macromolecule that is exceptionally resistant to physical degradation. Because the bacteria and fungi of that era had not yet evolved the specific biochemical enzymes required to digest this new, tough polymer, massive amounts of dead trees piled up in the stagnant, anaerobic swamps without decomposing. Over millions of years, the immense geological pressure of the shifting tectonic plates physically crushed and thermally cooked these undecomposed forests, transforming their trapped carbon directly into the massive subterranean coal seams that ultimately fueled human industrialization hundreds of millions of years later. Because the carbon was buried rather than oxidized, atmospheric oxygen levels skyrocketed to a terrifying 35%, allowing insects to grow to monstrous, terrifying proportions. However, the biological prosperity of the planet was completely shattered roughly 252 million years ago in an apocalyptic catastrophe known as the Permian-Triassic extinction event, or simply, the Great Dying. This event represents the closest the Earth has ever come to being completely, permanently sterilized, annihilating over 96% of all marine species and 70% of terrestrial vertebrate life. To determine the exact physical kill mechanism of this apocalypse, the British geologist and paleontologist Paul Wignall conducted extensive, highly complex stratigraphic research throughout the 1990s. Wignall's importance to the field of mass extinction dynamics is profound. He provided the detailed physical and chemical evidence linking the biological die-off directly to a massive, continental-scale volcanic eruption in modern-day Russia known as the Siberian Traps. For hundreds of thousands of years, the Siberian Traps violently erupted millions of cubic miles of boiling basaltic lava, physically burning through massive, subterranean coal deposits. This continuous, cataclysmic combustion injected incomprehensible quantities of carbon dioxide and toxic methane directly into the atmosphere. The sudden, massive spike in greenhouse gases triggered a runaway hyperwarming effect, raising the global ocean temperatures to physically lethal levels. In the physical sciences of thermodynamics, The behavior of dissolved gases in a liquid is governed by a fundamental law stating that the physical solubility of a gas is strictly inversely proportional to the temperature of the liquid. As the global oceans rapidly absorbed the atmospheric heat, their physical ability to hold dissolved oxygen violently collapsed. The oceans literally suffocated, becoming stagnant, hot, and completely anoxic. In this oxygen-starved abyss, highly toxic, hydrogen sulfide-producing bacteria thrived, belching massive clouds of poisonous gas into the atmosphere, simultaneously destroying the ozone layer and suffocating terrestrial life. The Earth was transformed back into a toxic, boiling hellscape, resetting the evolutionary clock and paving the grim, desolate way for the eventual rise of the dinosaurs. Following the apocalyptic desolation of the Great Dying, the Earth slowly and agonizingly recovered over tens of millions of years. The global tectonic engine had driven almost all the terrestrial landmasses together into a single, colossal supercontinent known as Pangaea. Stretching from pole to pole, this massive continent was surrounded by a single global ocean called Panthalassa. The vast interior of Pangaea was a harsh, arid desert, characterized by extreme temperature fluctuations because it was entirely cut off from the moderating, cooling effects of the ocean's moisture. It was within this severe, unforgiving environment that a highly resilient, highly adaptable group of reptiles known as the dinosaurs first evolved during the Triassic period, beginning roughly 252 as the Mesozoic era progressed into the Jurassic and Cretaceous periods. The relentless convective churning of the superheated mantle deep beneath the Earth's crust began to physically tear Pangaea apart. Massive rift valleys opened, and the global ocean violently flooded in, creating the shallow, nutrient-rich inland seas that characterized the era. The global climate during the Mesozoic was incredibly warm and tropical, with absolutely no permanent ice caps at the poles. The atmosphere was heavily saturated with carbon dioxide, continuously pumped out by intense, global volcanic activity as the continental plates fractured. This powerful greenhouse effect allowed dense, tropical jungles to flourish globally, providing the massive biological energy base required to sustain the absolute gigantism of the sauropod dinosaurs. For over 160 million years, these magnificent creatures completely dominated the terrestrial biosphere. However, their reign was violently terminated exactly 66 million years ago. The physical mechanics of this mass extinction were a highly debated scientific mystery until the year 1980, when a father and son team, the American Nobel laureate physicist Luis Alvarez and the geologist Walter Alvarez, published a profoundly important, paradigm-shifting research paper. The importance of the Alvarez team to the fields of geology and paleontology is absolutely monumental. They definitively solved the mystery of the Cretaceous-Paleogene extinction event by shifting the focus from slow, terrestrial climate change to a sudden, catastrophic, extraterrestrial impact. While examining a specific layer of sedimentary rock in Gubbio, Italy, that mathematically corresponds to the exact time the dinosaurs disappeared, the Alvarez team discovered an astonishing chemical anomaly. This thin layer of clay contained concentrations of the element iridium that were hundreds of times higher than normal background levels. In the strict realm of chemistry and metallurgy, iridium is a highly dense, incredibly hard, and highly corrosion-resistant transition metal belonging to the platinum group. Crucially, iridium is exceedingly rare on the surface of the Earth. During the iron catastrophe, when the young, molten Earth differentiated into physical layers, almost all of the planet's native iridium, due to its massive atomic weight, physically sank to the absolute geometric center of the planet, locking it forever in the metallic core. However, iridium is highly abundant in primitive, undifferentiated asteroids and comets. The Alvarez team mathematically concluded that the only physical way this massive amount of iridium could be evenly distributed across the entire globe in a single geological layer was if a massive asteroid had violently slammed into the Earth, vaporizing upon impact and blanketing the entire planet in radioactive, extraterrestrial dust. A decade later, in the year 1990, geophysicists finally discovered the physical smoking gun required to perfectly validate the Alvarez hypothesis, the Chicxulub Crater. Buried deep beneath the Yucatan Peninsula in modern-day Mexico, scientists mapped a colossal, circular impact structure measuring roughly 93 miles in diameter. Mathematical physics and supercomputer models dictate that the asteroid that forged this crater was roughly 6 to 10 miles wide. It struck the shallow coastal waters of the Yucatan at an estimated velocity of 45,000 miles per hour. The kinetic physics of this impact are almost incomprehensible. Following the fundamental mathematical law where kinetic energy equals 1/2 of the mass times the velocity squared, the sheer mass and astronomical speed of the asteroid resulted in an energy release equivalent to over 100 trillion tons of TNT, or roughly 1 billion times more powerful than the atomic bombs dropped during the Second World War. Upon impact, the kinetic energy instantly converted into a catastrophic thermal pulse. The asteroid itself, along with thousands of cubic miles of the Earth's crust, was instantaneously vaporized. A colossal shockwave violently propagated outward, instantly flattening tropical forests for thousands of miles. The impact physically displaced the ocean, generating terrifying, supersonic tsunamis towering hundreds of feet high that violently scoured the coastlines of the surrounding continents. However, the true global killer was the material explosively ejected into the upper atmosphere. The asteroid struck a specific region of the Earth's crust heavily composed of gypsum, a sulfate mineral. The immense thermal energy of the impact instantly vaporized this gypsum, injecting billions of tons of highly reflective sulfur aerosols directly into the stratosphere. Simultaneously, the trillions of tons of pulverized, superheated rock ejected into space began to rain back down upon the atmosphere, creating intense atmospheric friction that turned the sky into a glowing broiler oven, igniting massive global wildfires. Following this brief, intense thermal pulse, the dense cloud of sulfur aerosols, soot, and pulverized iridium-rich dust completely enveloped the globe. This physical barrier blocked almost all incoming solar photons from reaching the planet's surface, triggering an apocalyptic, global impact winter. Without solar radiation, the fundamental biochemical process of photosynthesis violently halted. The marine phytoplankton and the terrestrial forests rapidly died off. As the foundation of the global food web physically collapsed, the massive herbivorous dinosaurs starved, followed rapidly by the giant apex predators. In this dark, freezing, and barren post-impact world, absolute biological gigantism was a fatal flaw. The only terrestrial vertebrate creatures that survived this apocalypse were small, highly adaptable, and primarily subterranean. Among these survivors were the early mammals, endothermic, or warm-blooded, and capable of subsisting on a highly varied diet of insects, dead vegetation, and seeds. These tiny, rat-like creatures navigated the desolate ruins of the Mesozoic era. With the terrifying reptilian apex predators permanently erased from the evolutionary board, the biological stage was forcefully cleared for these surviving mammals to inherit the Earth, eventually radiating into the massive biological diversity that would ultimately lead to the evolution of human consciousness. In the desolate, smoldering aftermath of the Chicxulub impact, the Earth entered the Cenozoic era, beginning exactly 66 million years ago. With the massive, tyrannical reptilian predators permanently eradicated, the surviving mammalian species experienced a spectacular, rapid biological radiation. Without extreme competitive pressure, these small, highly adaptable endothermic creatures rapidly evolved to fill every vacant ecological niche on the planet, eventually diversifying into the massive terrestrial mammals, the airborne bats, and the fully aquatic cetaceans. As the Earth's biosphere recovered, the global climate underwent a drastic, highly volatile fluctuation culminating roughly 56 million years ago in a profound geological event known as the Paleocene-Eocene Thermal Maximum, or PTM. To fully comprehend the sheer scale of this ancient global warming event, the scientific community relies on the foundational research of the American paleoceanographer James Zachos. In the year 2001, Zachos published a highly detailed, continuous isotopic record of the Earth's climate spanning the entire Cenozoic era. Zachos's importance to the field of marine geology and paleoclimatology is absolute. He provided the definitive physical proof that the Earth's climate can experience sudden, catastrophic heating events driven entirely by massive injections of greenhouse gases. Zachos and his team achieved this by analyzing the microscopic calcium carbonate shells of benthic foraminifera, tiny, single-celled marine organisms that live on the deep ocean floor. By mathematically measuring the specific ratio of carbon isotopes trapped within these fossilized shells, scientists can perfectly reconstruct the ancient carbon cycle. In the strict realm of chemistry, isotopes are variant forms of the exact same chemical element that possess the same number of positively charged protons, but a different number of neutrally charged neutrons. Carbon-12 is the most abundant, lighter isotope, while carbon-13 is slightly heavier. Because biological life overwhelmingly prefers to utilize the lighter carbon-12 isotope during metabolic processes, a sudden, massive spike of carbon-12 in the geological record mathematically proves that billions of tons of organic carbon were violently injected into the ocean and atmosphere. During the PETM, geological evidence suggests that massive volcanic intrusions baked vast subterranean coal deposits, while warming oceans simultaneously destabilized colossal reservoirs of frozen methane hydrates buried in the seafloor. This cataclysmic release of carbon raised the global temperature by over 9 degrees Fahrenheit in a mere geological blink of an eye, turning the Earth into a sweltering, ice-free hothouse where tropical palm trees flourished as far north as the Arctic Circle. However, this hothouse Earth was not a permanent physical state. Beginning roughly 50 million years ago, a massive geophysical tectonic event fundamentally altered the planet's atmospheric chemistry. The Indian tectonic plate, accelerating northward at unprecedented geological speeds, violently collided with the massive Eurasian plate. The immense kinetic energy and geological pressure of this continental collision physically buckled the Earth's lithosphere, thrusting millions of tons of rock into the sky to forge the towering Himalayan mountain range and the vast Tibetan plateau. This colossal geological uplift initiated a powerful, global chemical thermostat known as the silicate weathering feedback loop. In the physical sciences, chemical weathering occurs when atmospheric carbon dioxide physically dissolves into atmospheric water droplets, synthesizing a weak carbonic acid. When this acidic rainwater relentlessly battered the freshly exposed, towering silicate rocks of the Himalayas, it triggered a continuous chemical reaction. The carbon was physically stripped from the rainwater, chemically bound to dissolved calcium and magnesium ions, and washed down massive river systems into the global ocean. Once in the ocean, marine organisms utilized these chemical compounds to build their shells, eventually dying and sinking to the abyssal plain, permanently locking the carbon away in massive layers of solid limestone. This relentless mechanical scrubbing of carbon dioxide from the atmosphere aggressively stripped away the Earth's thermal blanket, initiating a profound global cooling trend that eventually led to the formation of the permanent Antarctic ice sheet roughly 34 million years ago. As the planet grew progressively colder, it entered the Pleistocene epoch, beginning roughly 2.58 million years ago. The Earth became locked in a relentless, alternating cycle of advancing and retreating global ice ages. To explain the mechanical, astrophysical cause of these rhythmic glaciations, the Serbian mathematician and astronomer Milutin Milankovitch published his highly complex orbital theory in the 1920s. Milankovitch's importance to the fields of astrophysics and paleoclimatology is monumental. He mathematically proved that the Earth's climate is entirely beholden to the gravitational tug-of-war of the surrounding solar system, calculating precisely how slight geometric variations in the planet's orbit violently alter the distribution of kinetic solar energy reaching the surface. Milankovitch identified three specific, overlapping orbital cycles. First, the eccentricity of the Earth's orbit slowly stretches from a nearly perfect circle to a slight ellipse over a period of 100,000 years, driven by the massive gravitational pulls of Jupiter and Saturn. Second, the physical obliquity, or the axial tilt of the planet, shifts back and forth between 22.1 and 24.5 degrees over a cycle of 41,000 years. Finally, the axial precession, representing the slow, mechanical wobble of the Earth's rotational axis, much like a spinning top losing momentum, completes a cycle every 26,000 years. When these three independent geometric cycles perfectly align to mathematically minimize the amount of solar radiation striking the northern hemisphere during the summer months, the winter snowpack fails to melt. Over thousands of years, this triggers a runaway albedo effect, allowing colossal, miles-thick continental glaciers to physically march outward, crushing entire continents. It was during this highly volatile, freezing epoch that the ultimate biological apex predator emerged on the arid savannas of East Africa. As the global climate cooled, the dense, tropical rainforests of the African continent physically retreated, replaced by vast, open, and highly dangerous grasslands. In the year 1974, the American paleoanthropologist Donald Johanson made a discovery that permanently altered humanity's understanding of its own biological origins. Johanson discovered the remarkably preserved, fossilized skeleton of Australopithecus afarensis, famously dubbed Lucy. Johanson's importance to the field of evolutionary biology is absolute. His discovery provided the irrefutable, physical transition fossil proving that early hominins evolved obligate bipedalism, the mechanical ability to walk upright on two legs, long before they evolved massive, highly complex brains. By physically standing upright, these early ancestors minimized the surface area of their bodies exposed to the punishing equatorial sun and freed their hands to manipulate rocks and sticks. This anatomical advantage triggered an unprecedented, exponential evolutionary arms race. Over millions of years, the relentless evolutionary pressure of the shifting Ice Age climates forced the genus Homo to rely increasingly on intelligence and highly complex social cooperation over sheer physical strength. By physically harnessing the chemical combustion of fire and manipulating the environment through engineered tools, Homo sapiens finally emerged, fundamentally breaking the standard rules of biological evolution and preparing to become a geological force capable of reshaping the entire planet. As human civilization rapidly industrialized over the last 2 centuries, the Earth entered a completely unprecedented geological epoch. In the year 2000, the Dutch Nobel laureate and atmospheric chemist Paul Crutzen formally popularized the term Anthropocene to describe this new, highly volatile era. Crutzen's importance to the global scientific community is absolute. He chemically and mathematically demonstrated how human-manufactured chlorofluorocarbons were physically interacting with ultraviolet light to destroy the Earth's protective ozone layer, earning him the Nobel Prize in Chemistry. By defining the Anthropocene, Crutzen highlighted the terrifying reality that a single biological species, humanity, had become the dominant geological, chemical, and climatological force on the planet. By mechanically extracting and chemically combusting hundreds of millions of years' worth of buried carbon, in the form of fossilized coal, liquid oil, and natural gas, humanity is violently injecting billions of tons of carbon dioxide back into the atmosphere. In the physical sciences, this rapidly accelerates the greenhouse effect, aggressively trapping outgoing kinetic thermal radiation and threatening the delicate, 10,000-year climatic stability that allowed human agriculture and civilization to flourish in the first place. However, even if humanity successfully navigates this self-inflicted climate crisis, the long-term future of the planet remains bound to the ruthless, mechanical laws of geology and astrophysics. Looking deep into the geological future, the relentless tectonic engine powered by the Earth's radiogenic core will continue to physically reshape the continents. Based on rigorous geophysical models published by the American geologist Christopher Scotese in the early 1980s, scientists project that in roughly 250 million years, the current terrestrial landmasses will violently collide once again. Scotti's importance to the field of paleogeography is paramount. His computerized tectonic projections provided the very first mathematically accurate, predictive maps of the Earth's deep future. This massive future supercontinent, often referred to as Pangaea Ultima or Amasia, will feature a vast, hyperarid inland desert experiencing brutal, uninhabitable temperature extremes. The formation of this massive landmass will fundamentally disrupt global ocean currents, potentially triggering another devastating mass extinction event. Yet, the ultimate biological demise of the Earth will not be dictated by shifting tectonic plates, but by the physical evolution of our host star. In the precise realm of stellar mechanics, as a main sequence star like our Sun continuously fuses hydrogen into helium, its core slowly becomes denser and hotter. This increases the rate of nuclear fusion, causing the star's overall luminosity to gradually rise over billions of years. In roughly 600 million years, this steadily increasing kinetic solar radiation will dramatically accelerate the Earth's silicate weathering feedback loop. As global surface temperatures rise, atmospheric moisture and rainfall will increase, aggressively scrubbing carbon dioxide out of the atmosphere and permanently locking it into the planet's rocky crust as solid limestone. Eventually, the atmospheric carbon dioxide concentration will drop below the absolute physical minimum threshold required for C3 photosynthesis, the specific biochemical pathway utilized by roughly 95% of all current plant life on Earth. Without plants to chemically synthesize organic energy and free oxygen, the absolute foundation of the global food web will physically collapse. Terrestrial animal life will rapidly and permanently suffocate and starve, leaving behind only simple, microscopic extremophiles. By roughly 1 billion years from now, the Sun's luminosity will increase by a massive 10%. This overwhelming influx of thermal energy will violently raise global surface temperatures, causing the remaining oceans to aggressively evaporate. In the strict realm of atmospheric chemistry, water vapor is an incredibly potent greenhouse gas. As millions of tons of water vapor flood the sky, it will trigger an unstoppable, runaway greenhouse effect, completely mirroring the apocalyptic, boiling conditions of the modern planet Venus. High in the upper atmosphere, incoming high-energy ultraviolet photons will violently strike these water molecules, physically shattering the covalent bonds holding the oxygen and hydrogen atoms together. The incredibly light, solitary hydrogen atoms will easily achieve escape velocity, permanently bleeding out into the freezing vacuum of space and leaving the Earth completely bone dry. The absolute, final death of the planet is mathematically scheduled to occur in roughly 5 billion years. At this precise astrophysical threshold, the Sun will completely exhaust the hydrogen fuel in its core. The delicate physical balance of hydrostatic equilibrium, where the outward thermal pressure generated by nuclear fusion perfectly counteracts the inward crushing force of gravity, will violently collapse. The solar core will rapidly contract and heat up to unimaginable temperatures, igniting the fusion of heavier helium atoms. This explosive new energy source will force the Sun's outer plasma layers to exponentially expand, transforming our star into a terrifying, glowing red giant. The expanding wall of stellar plasma, burning at thousands of degrees, will violently consume the orbits of Mercury and Venus. Finally, the blazing stellar envelope will reach the Earth. The intense thermal and gravitational shear forces will violently melt the terrestrial crust, physically dissolving our entire world into the fiery, boiling interior of the dying Sun. The Earth, the only known cradle of biological life in the vastness of the cosmos, will be entirely, permanently erased from existence.